All right, so welcome to our final recitation session. Okay, so the topic is on cache. All right, and so you can get started here. Okay, so I will, as usual, go straight to the quiz questions. All right, and then from the quiz questions, you then look at some of the questions posted on the Slido. All right, and then we will take other things that you want to discuss. Okay, so in terms of cache, okay, so you've gone through the material, and so basically there are three general types of cache. One is your direct map cache, all right, which is the most straightforward one. Okay, and then your set-associative and then fully associative. All right, and if you again think about the whole idea of why we want cache, is comes back to the idea that your weakest link, okay, in your whole system is actually your memory access. Okay, your processor can run very fast. Okay, it can execute instructions at sort of gigahertz range. All right, but then you're always waiting. Okay, you're always waiting for data to be available to process it. All right. Okay, so that slows down the whole system. All right, so even though you can process very fast, you waste a lot of time waiting for the information, waiting for the data. All right, because if you look at all your code, what do you do? Most of the time you load from memory, you perform some operation, and then you store. Okay, you store the result. All right, so that in between operation is very fast, but then the load and store slows down the whole thing. All right, so that is where the idea of cache comes in. Okay, so again, it comes back to trying to keep as much information as we economically can close to the processor. Okay, so why we say economically can? Because some of you might think, why don't I just dump everything together? Correct? Why don't I just take the whole processor and take the whole memory that I want and just create one super chip? Okay, that everything is there together. Yes, technically you can do that. Okay, you can create such a chip, but the problem is nobody will want to buy it after that. Okay, why? Because people do not want to invest so much of money in a system where your processor is integrated with so much memory if I don't need that kind of memory. All right, so that flexibility is something that is wanted by developers. All right, they want to be able to take your processor, okay, and with a reasonably good performance, and then extend it to whatever memory that they want. Okay, so that's why we don't say that I sell you the processor a package together with a 4 GB memory, or a 32 GB memory, or whatever. Okay, we have only a limited amount of cache as internal memory to say that it helps the performance by a certain percentage. All right, so that is the general idea behind cache. Okay, so let's go into the question. Okay, so the first question is on the direct map cache. Okay, so in direct map cache, okay, so what we have is we have a memory of 4 GB. Okay, so we have 4 GB memory here. Okay, each block size is 32 bytes. Okay, so each block here is 32 bytes, and the size of the cache itself is so that's the memory. Sorry, then the cache itself, you have a 32 kilobyte cache. Okay, 32 kilobyte cache. Now we need to fill in all of these numbers here. So it's quite standard, all right? So if your block size is 32 bytes, okay, so we know that it's 2 to the power of 5 is 32. So the number of bits for the offset will be 5. So the offset is basically the last part in your whole address, all right? And that offset here in this case will be 5. Okay, so that is the telling us which particular byte we are referencing when we fetch one block of data from the cache. Okay, now for the next one, the number of bits for the block number. So for the memory, 5 bits are set aside for this offset. So the bits for block number will be 32 minus 5 should be 27. Okay, so number of bits for index. So index is basically number of lines here. Okay, so I will have a certain number of lines. Okay, that is basically your cache index, and that is the total size divided by the block size. So that will be 1 kilobyte. Okay, so 1 kilobyte is basically 2 to the power of 10. So you have 10 bits here. Okay, so what is remaining is your tag. So number of bits for the tag, okay, would be total of 32 minus your 10 minus your 5, which will be 17. Okay, so the number of cache blocks is equal to the number of is based on the number of bits for the index, correct? Because you have 10 bits for the index, means it becomes 2 to the power of 10. So it is 1024 cache blocks. Okay, and finally we are given this address and we want to find the mapping. So let's write out that address here in binary. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we know the tag is the first. Okay, or we say offset is 5 and then 10. So here to here will be the offset, then 10. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 10. So this is your tag. So this is the index. Okay, and then the rest of it is going to be your tag. All right, so it is I think quite straightforward. Okay, direct map cache. Okay, is what you have probably seen in your slides and your tutorial. Okay, so let's move on to the next question. Okay, so we only have 3 questions. Okay, so I think it's quite fast, and then we'll go to the Slido questions there. Okay, so we are given this 4-way set associative map cache with a block size of 4 kilobyte. The main memory is 16 gigabyte. All right, and there are 10 bits in the tag. Okay, so this main memory is now 16 gigabyte. All right, so if it is 16 gigabyte, how many bits are there in total? Okay, so total will be total of 34 bits. Okay, total of 34 bits for 16 gigabyte space. All right, so the 34 bits, how are we going to split it up? All right, so we know that the tag is 10 bits. All right, so I've already set aside 10 bits here for the tag. Okay, so left remaining here is total of 24 bits. Okay, so from this 24 bits, okay, what is the next information we know? We know that we have a block size of 4 kilobyte. Okay, so it's a 4-way set associative. So I will have 4 blocks here. I mean 4 cache blocks here, and each block size is 4 kilobyte. Okay, so each block size is 4 kilobyte. All right. Now, when each block size is 4 kilobyte, that means the offset, okay, the number of bits for the offset will be based on the block size. Correct. So 4 kilobytes is 4 times 1024, which is 1 kilobyte, which is 2 to the power of 2 times 2 to the power of 10. So it will be 2 to the power of 12. So you need 12 bits. Okay, so you need 12 bits for the offset. Okay, and that means for the set or the index, okay, index or the set, okay, we are going to have another, sorry, not 10, 12. Yeah. 12 here, so balance here will be another 12. So for the first question, the number of sets in the cache. So this number here, this 12 here is basically the number of lines, correct? The number of lines that I have here. And since I have 12 bits, so this is equivalent to 2 to the power of 12. Okay, which is the answer here, 2 to the power of 12. All right, that is the number of sets I have in the cache. So the number of sets is the number of lines you have in each cache. Okay, now what is the total size? The total size is, you first calculate 1, correct? So 1 of this one-way cache is, so 4 kilobyte is 2 to the power of 12, multiplied by how many lines? 2 to the power of 12 lines, which will be 2 to the power of 24. All right, and I have 4 of this, correct? So 4 of this would be 4 is 2 to the power of 2 times 2 to the power of 24. All right, so this is your answer, right? 2 to the power of 26. Now, how do I relate this to megabyte? Okay, so this is also one of the Slido questions. So let me come to that now so that we sort of get this out of the way. All right, so how do I sort of relate these numbers to the kilobyte, megabyte, and so on? Okay, so one of the easy ways is to remember some fixed numbers. All right, so we know that, okay, or one thing you can say is 2 to the power of 10 is considered 1 kilobyte, okay, which is equal to 1024. All right, so that is the first thing. Now, if 1 kilobyte is 2 to the power of 10, then how about, okay, 1 kilobyte, 1 megabyte. So 1 megabyte is equivalent to 1 kilobyte multiplied by 1 kilobyte, which is 2 to the power of 10 times 2 to the power of 10, which is 2 to the power of 20. Okay, so of course then you can add another, then become gigabyte and so on. All right, but coming back to this, so we know that 2 to the power of 10 is kilobyte, and 2 to the power of 20 is megabyte. Okay, so coming back here, I can say that for 2 to the power of 26, okay, it is equivalent to 2 to the power of 6 times 2 to the power of 20. Correct, because 2 to the power of 20 is megabyte, and 2 to the power of 6 is 64. So this would be 64 megabyte. Okay, so that is how you can easily relate the kilobyte and megabyte, okay, to power. Okay, so 16 gigabyte. Okay, so how do I get 34 bit? Okay, so we can come back to this same approach here. So 1 gigabyte will be 1 megabyte times 1 kilobyte. Okay, which will be 2 to the power of 20 times 2 to the power of 10, which will be 2 to the to the power of 30. Okay, so here will be 16 gigabyte. So for 16 gigabyte, it is equivalent to 2 to the power of 4 multiplied by 2 to the power of 30. So that's how you get 34. Okay, so let's go on to the last question. So the last question is about a fully set associative cache. All right, so we are given that the size of the main memory is 256 megabyte. Okay, so 256 megabyte, again, how many bits? All right, so it comes back to the same thing. 256 times megabyte. Megabyte is 2 to the power of 20. So 256 is 2 to the power of 8 times 2 to the power of 20. So it will be 2 to the power of 28. Okay, so we know that 256 megabyte is 28 bits. Okay, so the cache memory is 16 kilobyte and the block size is 256. So if the block size is 256, so 256 means it is 2 to the power of 8. So 8 bits is set aside. Okay, so 8 bits is set aside for the tag. Okay, which means the sorry, not tag, offset. The 8 bits is set aside for the offset. So whatever remaining is the tag, which is 20. Okay, so in a fully set associative cache, any entry can go to anywhere in the cache. Okay, so you only have the tag and the offset. Okay, so again, the idea of cache is quite straightforward. Like I said, the only thing we just need to know how to do this, some basic calculations in terms of the direct set associative and fully set associative. Okay, so let me go to the Slido questions. Okay, so for the first question, I think we already can see that it is not always 4 gigabyte. Okay, so as what we saw in the questions, it can be bigger, it could be smaller. So we just need to go back and calculate how many bits we need to use to access that memory. Okay, so why is the main memory on a DRAM instead of hard disk? Okay, so what is the hard disk use? Okay, so it's always from the slowest to the fastest. All right, the fastest memory. Okay, so if you take your processor here, okay, the fastest sort of access is your registers. Okay, your registers. Okay, your S0, S1, okay, T0, T1, whatever that you use for your processor. Okay, those registers are part of the already interconnected with the processor architecture for you to have immediate access to them. All right, so that is your fastest access. Now the slowest access is the one that is you put away at the sort of furthest, and that is your hard disk. Okay, so hard disk is in general the slowest device. All right, but it is very cheap, so it holds a lot of information. All right, and in order for you to execute code and for you to load information more quickly, we have your DRAM, okay, which you consider as your main memory whenever you want to run any application. Okay, so whenever you want to load, okay, let's say for your PowerPoint, your Zoom, whatever application you run, you extract that software, that application from the hard disk and you load it onto your DRAM to start executing. Okay, so of course your processor, when it talks to the DRAM, is also a slow interface. Okay, so that is where we bring in the idea of the cache. Okay, so inside your whole process architecture, we bring in the idea of the cache, okay, to make it faster for data that is either having that spatial locality or temporal locality. All right. So even though we study this idea of a unified cache, okay, if you look at most modern architectures, they have instruction cache and data cache, okay, to sort of take advantage of instances where there is locality in either instance. Okay. All right. So that is the idea of DRAM. So we say that the DRAM is considered the main memory because that is the working memory when you are executing any application on the system. Okay, this one conversion we already covered. Okay, so for block size trade-off, why only temporal locality suffers? Led to miss rate. All right, so when you say you increase your block size, okay, when you say increase the block size means every time there is a hit, okay, you fetch a bigger block of data and you bring it in, correct? So which means that for data that is close together, it is good, okay? But when there is data, when there is a miss, what happened? When I need to reload this cache with a new data or reload this block with a new data, all right, then I have more sort of data to fetch and fill up the cache. Okay, so that is why the temporal locality suffers, all right, because when the data is not within that same instance of locality and I need to reload the cache, then the time taken, okay, to reload the cache is higher because it's a bigger block size. All right. Okay, so this slide here, all right, cache slides. Okay, let me take out that slide. Give me a minute. Okay, so maybe if you look at the slide, it'll be easier. Give me a minute now. Okay, so I think this is the one where students have questions. Okay, so if you look at this, when I have a larger block size, like I said, we take advantage of this spatial locality. All right, that means there is more data that is closer together. So when there is spatial locality, I have this bigger advantage. Okay, but because the block size is bigger, when I miss, that means I take longer time to fill out the block. All right. Now, if the block size is also very big relative to the cache size, means I have lesser blocks that I can hold. Okay, because your cache size is fixed, right? You have a certain amount of cache size that you have. And if I say that my block size is very big, okay, then the number of blocks that I can hold is smaller. So if the number of blocks that I can hold is smaller, then the chances of me missing are higher. Okay, is higher. So that is why, okay, there is a sort of a trade-off here, okay, between the spatial locality and temporal locality. All right, so that is why this, that's what this slide is trying to explain. All right, when my block size is too big, I hold lesser blocks. When I hold lesser blocks, which means that there's a higher chance that I will miss, all right, okay, because of the temporal locality. Okay, I think so. Those were the questions here. Okay, so for cache miss, all right, the basic way to look at it is simple. Whenever you have the very first time that you miss, okay, for example, okay, so the very first time that you load a data, okay, to a cache, all right, that means when the cache is easily empty, that is called a cold miss, all right, or a compulsory miss. All right. The conflict miss will occur when that data or that line is currently occupied. Okay, but then there is another data that is supposed to take over because it matches in terms of the index, but the tag is different. So I need to sort of get rid of the current data and replace it with the new data. Then we say it's a conflict miss. All right. The capacity miss is the case of the fully associative cache, where any data can go to any cache line. Correct. So the capacity miss is when you have fully exhausted all the available space. All right, and then you have to evict one of the current entries in your cache table. Okay, so that is basically the three types of misses that you have. Okay, so there's some questions about this as well. Where do you have this additional bit? All right, the valid bit, okay, and so on the dirty bit. All right, so when we look at the cache size so far, we only considered the actual data that we want to hold. All right, so by right, you also need additional space, all right, for the valid bits and so on. Okay, so for example, okay, if I come back to one of the slides here. Okay, so you can see that when I say 16 kilobyte cache forward 16 byte blocks, all right, we are actually only referencing the forwards here, the data. All right, but I also need to factor in the total cache size that I really need has to factor in the amount of space for the tag plus the valid bit. All right, so the actual cache size is of course bigger. All right, but when we generally mention cache size, we are actually just making reference to the data that we are holding, the actual words. Okay, that means the information we copy from the memory. All right, but the actual space is more than that. Okay. Okay, so with the right bits, okay, so this is again referring to this slide over here. All right, so if you notice, we always have a multiplexer, okay, to extract out the word that we want. All right, so the word that we want, okay, again, the last two bits will always be 0, correct? It's always a word access, correct? So in a sense, you can say that you only need the last, you can ignore the last two bits and take the remaining bits. Okay, that is why over here, for example, I only need to take the bits 3 and bit 2, okay, to know whether I'm talking about word 0, word 1, word 2, or word 3, because the last two bits will always be 0. All right, so that sort of wraps up. Like I said, it's a short session, okay, and only 3 questions. Yep, so that sort of wraps up everything. Yeah, so we have no more sessions, and rest is for you to get prepared for the exam. Were there any past year papers uploaded on the Canvas or anything? So I haven't checked yet. So I think you always download past year papers also from the library portal. All right, and use that as a gauge, correct, to see kind of questions. I think even in the tutorial we have also given past year paper type questions. Okay, so you have a feel for what is expected. All right, so I think you also saw the announcement we will be using ExamSoft, I mean Exemplify. All right, so make sure you have tested it and ensure that it works. All right, other than that, any other things that we need to tell you? I think probably Colin will send an announcement. Okay, so it has been nice having you all around, okay, for this semester. Wish you all the best, okay, for the exam. Yeah, so if you have any questions, you feel free to, I mean, you can put in the Telegram chat, or you can contact me, all right, or any of us, me, Colin, and Prabhu, and we'll be happy to help you all out. Okay, so all the best. I'll still stay around if any questions you all have. Okay. Okay, so give me a minute. This cache slide 87 is there is no 87. Which slide are you referring to? Okay, so for the cold mist, all right. So I think there is some issue with the slides, all right, with some of it being called cold mist when it's supposed to be a conflict mist. Okay, so this one I will check with Prabhu, ask him to update you all, okay, on the slides. Cache 2 slide 18. Okay, wait, let me go there. Cache 2 slide 18. Okay, wait, let me share screen first. Okay, so for this one, the first axis is a cold mist. Okay, the next one is also a cold mist. Okay, this is also a cold mist. All right, so this one, more previous slides as in the cache one, is it? Slide 12. Okay. Yeah, so first two is considered yeah, I think this one, the first one is only considered cold mist. The rest should be considered conflict mist. Yeah, so the cold mist should be only the first access. Subsequently, the rest is all conflict mist because they all come back to the same cache index. Okay, so the other question is quiz question 1, part 6. Okay, so part 6 is basically you are given this address, correct? 0x1234578, which I just wrote it from hexadecimal directly translate to binary. And since we already know from the earlier calculation that the 5 bits, last 5 bits is offset, then another 5 bits, another 10 bits for index, and the remaining is stacked, then you just sort of separate accordingly, and then you get the bits. Yeah, correct. You just convert the hex to binary and split. Because so the hex is, how are the bits for index? Okay, so the number of bits for index. So index is basically the number of lines that you have. Right? So your total cache size that you have is 32 kilobyte. Okay, and we know that each block is 32 bytes. Okay, so you take the total size over the size of each block. So you get 1 kilobyte. And 1 kilobyte is 2 to the power of 10. So that's how you get 10 bits for index. Okay, so any other questions?
May I ask a question, Prof?
Yeah.
So I was looking at these slides and I'm very confused between the direct map cache. I also watched the videos, but like I'm still very lost regarding the cache and memory. Like, what is this for that they're talking about when they say they, for example, slide cache 1, slide 55. Like the addresses, this 408, 12, and 36.
Okay, so this 408, 12. Okay, now. So this is basically the address that you want to access. Okay, that means I want to access address 4. Okay, so when I want to access address 4, okay, it means what? That means I am looking at what is the address 4. That means address 4 is this value, correct?
So this address 4 is in the memory.
Binary. No. This is the address of the memory that I want to access. Okay, that means what I'm saying is now my processor wants to get some data from an address location, and that address location is address 4.
Okay.
So this information, this value 4. So value 4 in binary is this, correct?
Yes.
Okay, so this goes out on the what we call the address bus of the system. Okay, so if you think about it, basically what is happening is, okay, when I have an address, okay, when my processor wants to talk to my memory, okay, there is two, I mean, there are a few different things, but the basic thing is I first need to tell it where or which memory location I want to get data from, correct? So that information is actually what we call the address information. Okay, so if let's say I put out this value 0x0004, that means I am telling the memory I want to get the information in address location 4. So inside address location 4, okay, let's say this is address location 4, there is some data, correct? Okay, so let's assume that data is 0x55112233. Okay, this information that is inside this memory location 4 will be read, and it will come out through another bus known as the data bus. Okay, so that is what memory access is all about. Okay, I give an address. Okay, from the address that I give, the memory will process that address to sort of give me the data in that location and send it back to me through the data bus. Okay, now the whole idea of cache is, instead of always having to go out to the memory to get this information, why don't I keep some copy of this internally here, so that instead of all the time, every time going out, I can try to just do a read and write within the internal space. So that is the idea of the cache. Okay, so over here, basically what is happening is all these addresses that you see are, in a sense, pointing to the actual memory. So you can see this is the idea of the memory. Okay, so when I first put out the address 4, okay, so if the cache is initially empty, means then what I need to do, I need to go to the actual memory, like what I showed you just now. I take the data and I bring it back. So when I bring it back, what I do is I create a copy of that data, okay, inside my cache. Okay, and then I keep repeating the process. Only thing is, once I start filling up data with my cache, whenever I want to do a memory access, I check whether that copy is already available within the space in the cache, so that I don't need to waste time going to the external memory.
Okay.
So basically that's the idea of cache. That means I every time give you an address, I say I want to access the data in this address. And what does the cache system do for us? It checks within itself, okay, whether I already have a local copy. Then if don't have, then I go out. It's just like, for example, you carry a wallet with a certain amount of money, correct? Okay. And
Yeah.
the idea of the wallet is what? When I need to use money, I have a certain amount that is close to me. Okay, maybe $50, $100, whatever. Okay, you don't empty your bank balance and carry $10,000 in your wallet. You keep $9,800 in your bank, and you maybe draw $200. Correct?
Yes.
So it's the same idea. Only when your $200 finish, then you go back and you take some more. So it's the same idea. So this cash is like a wallet. You keep whatever that you need for this current instance of time. Okay, but if for some reason you need more, that means it is not there. Okay, what you expect is not there, then you go and get that new data. So it's the same thinking. Only thing is here is data. So when the data that you want is already within your cache, you save your time. You don't need to go out. Okay, but if it is not in your cache, then you have to go out and then you keep that copy inside your cache so that it becomes easier. The next time round, I need the cache. I need the data.
Mm. So for this example, it is 2 words, so it's 8 bytes.
Yes.
So it's how do I say?
So since I have 8 bytes, so the 2 to the power of 3 is 8. So that's why I use 3 bits here.
Oh, okay.
Then the index in this case is again comes back to how big is your cache size. All right. So in this case, we so in this case, this is the example. So the cache index is 2 bits. Okay, so that's why we have 4 lines.
Oh, I see.
So, so this is power of 2, 4. So the 4 lines are here.
So this is the size of the cache block.
So the total size of the cache block is basically, you can say, as 4. I mean, the total size is considered as 8 times 4, 32 bytes.
2.
Because one block here is 8 bytes, correct?
Yes.
And you have 4 blocks, so it's considered, total size is considered 32 bytes.
Okay.
Yeah. So that's the idea of cache, right? So of course 32 bytes is very small. All right. If you have a bigger cache and you can hold more information, then it will be, in a sense, better that you don't have to maybe go out so much.
Oh, okay. So that means the 16 kilobyte cache block, is one block of cache 16 kilobyte means you need like 10 bits.
Yeah, that means 10 bits is the offset. No, 16 kilobyte. 16 kilobyte is 14 bits.
14 bits.
Where did you see 16 kilobyte?
This is the cache 1 slide 28. The calculation. 28. Yeah, this one, the 16 kilobytes.
Yeah, so one block is 16 bytes, not 16 kilobyte.
Oh.
One block is 16 bytes. That means inside this cache, okay, so if you look at it, I have a total of, so the total cache size here is 16 kilobyte, correct?
Yes.
One block is 16 bytes. That means one block here is 16 bytes.
Okay. Which is the one that we saw just now.
Just now was 8 bytes, 2 words. 16 bytes is 4 words.
Okay.
All right, and 16 bytes, so 16 kilobyte divided by 16 is 1024. That means I have a total of 1024 lines in my cache. That means this 10 bits is used to tell me which line I'm referring to.
Oh, okay.
Mm.
Okay. That makes more sense now.
Mm.
So the tag is just to match.
Yeah, the tag is to match. So when, for example, I read from data, I read from memory. So the index will point to a line, because the index number of bits is basically the number of 2 to the power number of bits will give you the total number of lines. So I have 10 bits, which means I have 1024 lines. Okay, so the 10 bits on the index will point to one of the lines. Then I will be able to access the data in that line, correct?
Yes.
Now the next thing I need to do is I need to check whether it's valid. That means there is already data inside this cache. And then after that, I need to check whether the tag matches. Correct? Because the tag could be the same or could be from a different tag, correct?
Yes.
Because a different memory could have a different tag. Okay, so I need to check whether the tag matches. If the tag matches, all right, and it's a valid bit is set, that means what? That means I have already accessed this memory chunk before, this memory block before, and it's already in my cache. So since it's already in my cache, okay, then I say it's a hit. So then I look back at the offset and decide which of these 4 words I want to access. Because in one block I got 4 words, but I only want to access 1 word at a time.
Okay. I see. Oh, okay. So that means this tag index and offset is basically the memory address. This whole thing is the memory
this whole thing is a
address.
memory address.
Okay. Thanks.
Yeah, so yeah, it's the same concept only. It's always the same memory address. It's just that depending on how we design the cache, we use different bits for the tag, index, and offset. That's all.
I see. And then also the hit and misses are also like controlled because of the different type of caching system, right?
Yes. I mean, in a sense that if it's a hit, then we take from the cache. When it's a miss, then we take from the memory, copy it to our cache, and then do the memory access one more time.
One more time.
Because the first time is a miss, correct?
Yes.
So I have to go out to the memory, take the data, bring it back to my cache, and then run the instruction one more time, or do the cache access and then get the data.
Miss.
Yeah.
Oh, I see. Okay. Miss penalty. Okay.
So yeah, so that is considered a miss penalty because you miss plus so because you miss, you need to factor the first access plus the reload.
Okay. I think I'll rewatch the lectures again.
Yeah. It is yeah, maybe you just got confused with that the words, terminology.
Yes.
Yes. So but the concept is the same. You just have that same address and then you sort of use it around for different sizes of cache, and then you design the usage differently. Have you done the tutorial already this week?
No, not yet.
So probably you can go through the lecture and then try these examples, and then if you still have doubts, maybe you can ask your tutor to clarify further.
Okay. Thank you.
Okay, thank you. All the best.
Thanks.
Okay, bye.
Bye.